So this lesson, we're going to work with exponential expressions, equations, and formulas. So some things we're going to be looking at, we're going to be basically evaluating exponential expressions, mostly using a calculator. We're also going to introduce this special number E, working with E, and that's pretty much what we'll mostly focus on, is all those main two. When it comes to an exponential function, what we're getting into is we have essentially, remember how we did function notation, if we have f of x equals 2x, notice this is a degree 1 equation. You want to make a table of this, we use -1, 0, and 1. So when I put it, 2 times -1 would have been -2. 2 times 0 would have been still 0. If I put a 1 in for x, 2 times 1 would be 2. So if I graph those order pairs, -1, -2 would be here. 0, 0, and 1, 2 would be here. We'd have a graph. Since this is a degree 1, this would be linear. So our graph would kind of take on, let's see if I can get this graph here to show up. So our graph would kind of pass through those 3 points like so. That would be what we call our linear equation. Now, if I create another function, g of x is equal to 2 to the x. If we do this function, if we put -1, 0, and 1 in again, this now becomes 2 to the -1, which actually represents 1/2. A negative exponent, -1, means to take the reciprocal. So that would be a 1/2. If I put a 0 in, 2 to 0 is another special exponent. Anything to the 0 power would be 1. And then if I put 2 to the 1 in, 2 to the 1 would just be 2. So when I put 0 in, I got 1. And then if I put a 1 in, we get a 2. So if we graph these 3 order pairs, we'd have -1, 1/2, 0, 1, and 1, 2. So the graph would kind of take on this. Look, notice how it's not really linear. There's not any consistent slope movement between points to points. It changes a little bit. If I want to graph a few more points, say if I graph, say 2 to the second power would be 4. And if I pick 3 to the third power would be like 8. So 2, 4, and then 3, 8 would be up here. So essentially this graph takes on, as I come down through here, this graph will kind of come down and bend, and it'll kind of start to turn like that. So that's going to be the graph of our exponential function. It's going to be more of a curved looking graph. So we have that kind of going on here. So these are the kinds of functions we're dealing with, this exponential growth. Notice that exponential growth is a much more rapid growth than a linear equation. Here and here it kind of starts out the same, but as x gets larger, notice that the y's get really, really large in a hurry. And that's what we call exponential growth. So one of the things you'll be doing in this section is working with the calculator. So let's see if we make sure we can do 5 to the 6th power, 4 to the -3rd, and 8 to the 2.5. So 5 to the 6th means 5 times 5 times 5 times 5 times 5 times 5. So that gets to be rather big in a hurry. So if I hit enter, notice how that would actually be 15,625. So it don't look like much, but 5 to the 6th power becomes a really large number in a hurry. 4 to the -3rd, so if I do 4 raised to the -3, notice how that actually becomes a really small number in a hurry. So it's going to be 0.01525. And 8 to the 2.5, 8 to the 2.5. So notice how that one, we almost have to probably end up rounding it. It's probably what happened on that one. So that's going to be 181.0195. probably just round it to the fourth decimal place, 881.0193. So we get some really unusual numbers with these exponents. So that's one thing we'll pick up on as we move into some of these lessons is we don't get these normal numbers that we're used to. So one of the first things we're going to do with exponential equations is we're going to work with what we call compounding money. So A is described as the amount accumulated, or we also call this our future value. So A is kind of our future value, our final amount. P is our original principal, or our present value, if you will, what we have now, what we start with. T is time in years. R is the interest rate per year. And usually it's going to be expressed as a decimal. So if they gave you 7%, we have to change that to 7 divided by 100, or in other words, 0.07. So remember, when you divide by 100, you move the decimal 2 places to the left. N is going to be the number of times compounded in a year. So in compounding interest. So we'll have to pick up on some vocabulary words there as we move on. So this formula is how we actually calculate compounding interest. So like in a savings account, if you have a savings account, a lot of times it's compounded monthly or quarterly. This is a formula you would actually be using in that sense of compounding. Now, the catch is you're not allowed to keep adding or taking away money. It has to stay put for this formula to work. So this is why this formula is kind of basic in that sense. So because we're not able to change the principal, the beginning amount, we just have an initial investment and then we just kind of watch it grow. So using the formula A equals P times 1 plus R divided by N raised to the NT, along with the graphic calculator, we can find the accumulated amount of an investment of $1,500 invested at an interest rate of 9% for 3 years if the interest is compounded quarterly. So again, what we're looking for is our final amount, our future value, if you will. The principal is the present value. That's how much we started with. So our present value was the $1,500 that we invested. Our interest rate was the 9%, but that's got to be turned into a decimal, so it's going to be 0.09. Our time is in years, so that's going to be 3 years. And then our N is the number of times compounded in a year, and that's where the word quarterly comes in. So quarterly means 4 times in each year. So we have what's called semi-annual. Semi-annual N would equal 2. Quarterly N would equal 4. Monthly N would equal 12. Daily N would equal 365, or sometimes there's what's called the banker's rule, which would be 360. So if I want to find my future value, what I can do is substitute into our formula these values. So A equals, the principal is the 1,500. In parentheses, we have 1 plus, then our interest rate has got to be a decimal, so it's going to be 0.09, divided by the number of times compounded in a year, so it's going to be 4. And we raise that to NT, which is going to be 4 times 3. So if you want, we can clean this math up, or we can just put it all in the calculator as is. I'm just going to put in the calculator as is, so 1,500. And then in parentheses, have this 1 plus then this 0.04 divided by, 0.09 divided by 4 raised to the 4 times 3, which would also have been 12. So if I enter, I should get a number that's more than 1,500 because we're investing. So our future value should be more than what we started with. So notice how we ended up within future value after 3 years would be $1,959 and around 7 cents if we round to the nearest penny. So notice how we made around $459.07 in interest. So that's one thing about money. Money can make money. in certain environments. That's why a lot of people like to use the stock market, is because in the stock market, your money has the ability to make money. But remember, this is all risk. Things can also lose money. It's not always a win situation. So we have some other formulas here to find compound interest. We have, A, as I said, kind of stands for future value. P is the original amount or present value. R is the interest rate per compounding period. N is the total number of compounding periods. So we also could have a formula that looks like this. A equals P times 1 plus R to the N. So they can kind of modify that a little bit. And we also know that if you subtract the original principal from the accumulated amount, that will give you what we call interest. So the final amount minus the present amount, the original amount, if you subtract those, that tells you how much interest is earned. So what I can do is I can create a formula to calculate interest as well. So I can have P times 1 plus R to the N represents my future value. If I subtract my present value, that will give me my interest. So I can also make it look like this. P times 1 plus R to the N minus 1. So what they're doing there is these both have a P in common, and I can actually do some factoring there as well. So there's some things we can do. So if I want to find the compound interest of an investment of $10,000 at 2% annual interest, compounded semi-annually for 3 years, what we can do is we can use this formula here, or we can, just also we can just kind of use the original formula. So if I have A equals P times 1 plus R over N to the NT, that'll tell us what our final value was. So notice how our A we don't know. The P was the initial investment, which is the 10,000. The rate was 2% or 0.02. The time was 3 years, and the number of times compounded was 2. So we have this 10,000 times then 1 plus R over N. R over N would be the 0.02 divided by semi-annually is 2 as well. To the NT, that would be 3 times 2 or 2 times 3. Notice how the R over N represents the interest being earned in our formula up here. So notice how this is going to be R, and 2 times 3 is going to be our N, because that's the number of times actually being compounded all together. So you can start to kind of see this formula materialize in this formula here. So anyway, if we have this 10,000, 4 zeros there, and then if we multiply that times 1 plus 0.02 divided by 2, and then to the NT, which would have been 2 times 3. That should be an exponent, though. Delete that all off. Raised to the 2 times 3. That'll tell us how much we made. So A would actually be $10,615.20. So my interest is going to actually be A minus P. So it's going to be the $10,615.20 subtract the 10,000, and that would just be $615.20. That'd be our interest that we made over the time. Now, what they're wanting us to do is pick up on these other formulas, but it's easier just to probably keep it in this format right here, but we can combine these formulas to make this formula here. But we have to pick up on, though, that, R is the interest rate per compounding period. So we would still have to use the R over N in our original formula up here to do that. So it kind of gets modified. So anyway, I find these formulas probably no real use to us at this point, without having to do some other math along with it. So that now this is why they're getting into this right here. So, it's like, whoa, maybe we want to rediscover these guys up here. So keep in mind, capital R is R over N, and capital N represents NT in our formulas here. So we have some other math to do if we're going to use these formulas here. So to find present value, they use PV, which is also the same thing as P. And future value is really also the same thing as A, if you will. So they just like to use those values there. But, present value and future value is like our final amount. So those are very similar in nature. PV is the same thing as P, and FV is the same thing as A in our formula. R, like I said, is the same thing as R over N. So notice how this really is P, this is really A, and the number of compounding periods is actually N times T. So there's some things that are tucked away in these formulas here. So if I want to do this example here, in the seventh inning, Sports Shop needs $20,000 in 10 years to replace engraving equipment. Find the amount the firm must invest at the present if it receives a 5% interest compounded annually. So notice how annually just means compounded one time a year. So let me just figure this out of my way. I can't get to my pins. You probably can't see that. All right. So what they want to know is we need to end up with 20,000. What we're asked to find out is, what do we need to invest now? So this is going to be this present value equals the future value over 1 plus R to the N. So again, R represents R over N. So notice our rate was 5%. Compounded annually means just 1. Well, 0.05 divided by 1 is just still 0.05. Capital N here, N is the same thing as N times T. So notice how we're just compounding one time a year for 10 years. That's just going to be 1 times 10, which would be 10. So to find my present value investment, our future value is going to be the 20,000. And we're going to have this 1 plus R, which is 0.05, raised to the N, which was 10. So if we do that math there, that'll tell us what we need to invest at this point here to make the 20,000 in 10 years. So I'm going to use the alpha button. So I'm going to put the 20,000 on the top. And then on the bottom, I'm going to have in parentheses 1 plus 0.05, or you could write 1.05 if you wanted to, raised to the 10th power. And if I hit enter, that tells me that I need to invest now $12,278.27 basically. So we have to kind of have a little bit of an egg set up there to get the 20,000 in the end. So in 10 years, our money would have made the rest of the money up. So that's what you want to kind of do. is if I just set aside this money and let it earn interest, it can allow me to have my money I need in 10 years ready for us to use. So another thing we're going to get into is what's called the natural exponent, which is also called E. E is a lot like pi. It's a constant. So remember, pi represents 3.14. E is also a special number. And the way the E comes into play is, you may recognize this a little bit now, is this 1 plus 1 over n to the n. This expression we kind of see in finance. As n gets larger and without bound, the value of E starts to get close to this value right here, to 9 decimal places. So I'm used to writing it as simply, not that far out, but I'm just writing it as 2.71828. I'm pretty good with writing it out 1, 2, 3, 4, 5 decimal places. But notice how it basically does 71828, 1828 again. So it does that 1828 as a repetition there. So that's what we call the number E. Notice E is on your calculator in 2 spots. Notice how there's this E in the division area spot. So if it's second division symbol, that puts an E into the calculator. If I hit enter, notice how it gives me this 2.718281828. It goes out 9 decimal places, just like they do right there in that. So E is what we call a natural number, and it does exist on our calculator. So another place to do it is, notice how it's above this ln symbol. There's this e to the x. So an easy way to put e to the 2.7 into the calculator is actually hit the second ln button, and it already prompts us to put an exponent in there, 2.7. So what gives us then 14 point, if we round this to 3 decimal places, 14.879. That would be, actually that 9 would actually round, and that would actually round on up to 80. So since there's this around to this 9, there's a 7 after it, so that 7 now has to round up to an 80. So 14.80 would be that. If I want to do e to the negative 3.2, if I hit the second button, hit the ln button, it has this little e, and it's prompted for an exponent. If I put negative 3.2 in there, hit enter, it'll give me that value. Again, if I do that out to 3 decimal places, that would be 0.041. Since there's a 7 after that other 0, that's going to make that move into a 1 spot. So we can evaluate some strange looking expressions with the calculator. So another thing we got is, the formula for the atmospheric pressure in millimeters of mercury is P is equal to 760 times e to the negative 0.00013 h, where h is the height above sea level in meters. Find the atmospheric pressure at 100 meters above sea level. So P stands for pressure. So to find the pressure, I have the 760 e to the negative 0.00013. And notice how they gave me what h is. It's going to be a 100. So I can actually type this into the calculator. The 760 times e, and I'm prompted to put that exponent in. So negative 0.00013 times 100. If I hit enter, that'll give me the atmospheric pressure. So if we round that to the nearest whole number, that'd be 750. So it's going to be millimeters of mercury. So back in the day, they actually had, thermometers and stuff made out of mercury, which react with temperature as well. So another thing we can do with exponential problems is we can find a cumulative amount, future value, for compounding, what's called continuous compounding. So for compounding continuously, we have this formula here. A is equal to P times E to the RT, where again, A represents the future value or our final amount. P is our present value or the principal. R again is the rate per year, but notice how the rate again has to be in a decimal form. And then we have time in years. So example 11, if it says find the compound amount of $5,000 invested at an annual rate of 4% compounded continuously for 5 years, this word continuously is the cue that we're going to be using this formula. A equals P times E to the RT. Sometimes I call it PERT. There used to be a shampoo, I don't know if it's still out there, called PERT, but that's the compounding continuously formula. So P is going to be the initial amount, which is the 5,000. The R was the 4%, 0.04. And we don't have to worry about N because we're talking about continuous compounding. So we just need to know the time, which is going to be 5 years. So A is going to equal then this 5,000 times E raised to the 0.04 times 5. So if I use that in my calculator, I can determine the compounded interest or the final amount. So give us then, A would be 6,107 and a penny. So that would be our future value. All right, so that gives you a little bit of an idea of how to work with some exponential types of math, especially with some formulas in finance.